अब नजर आ रहा है आप लोगों पे?
नो सर, स्क्रीन शेयर नहीं हुई।
अच्छा, स्क्रीन शेयर नहीं हुई, ठीक है सर। मैं वही है ना कि मैं अगर कुछ चीज चेंज करता हूँ तो स्क्रीन शेयर अब हो जाना चाहिए। अब आ गया?
यस सर, अभी आ रही है।
ठीक है, सही है। सो लेट्स बिगिन। Last time, so I have repeated basically this setting because these random variables they all arise from Bernoulli sequence of trials. So just to make sure that you are familiar with the terminology, I just repeated that part. Yeah. So I have a sequence of Bernoulli trials. Actually, I forgot to fix this, but this should not be limited to n trials. Yeah. You can think of it as a Bernoulli sequence of trials. Yeah, a sequence of Bernoulli trials, because sometimes this has to be infinite. You saw it for geometric. So you just think of it as a sequence of Bernoulli trials. And one more thing is that we have defined for each trial. मोमल, ये आप गलती से कर रही है?
जी सर।
ये गलती से ये आप क्लिक कर, ये आ रहा है कि मोमल इज रिक्वेस्टिंग कंट्रोल।
जी सर, मैं बिल्कुल गलती से।
अच्छा अच्छा, नहीं खैर ये कोई मसला नहीं है, बस वो आउटसाइडर कोई ना हो सर। तो अब so for each trial I we have a success indicator xi which is Bernoulli distributed. So this is also nothing new. One thing nobody asked me so far, if you remember when we did not start these random variables and we would have different experiments like trial 1, trial 2 and so on. Let's say these are different experiments. Yeah, trial 1 or trial 2 and so on. So because they are different experiments, they will have different sample spaces, and we try to use different probability measures. So like for example P1 and then P2 for the second one. Yeah, do you remember that? And even conditioning, I write 2 given 1 and so on. We don't need that here. Why? Can anyone guess why we don't need that here? The reason is this. We have a combined probability space. Yeah. So this sample space is already the combined space. So even if I define let's say x1 as a random variable which only focuses on the first trial, the sample space is still for all the trials, the combined one. So I will have a common probability measure P. I don't need it. Yeah. So when I say P of X equals to something, that P is not just for the first trial, that P is for the combined. Are you getting this? This means that we don't care about actually those different trials. We have a combined space, probability space, combined sample space, combined sigma field, combined probability measure. That's why we will always write this P. So that's actually, and this is only possible because we are using random variables. It was not so easy without random variables. So let's move on to the questions. These were the four, actually not questions, these were the four quantities which we were interested in, and we were done with these first two. Yeah. So this was done. Yeah. That turned out to be a Bernoulli random variable, if you remember. Yeah. And the second one turned out to be a geometric random variable. Actually, I got this one wrong. This should be 1. Yeah. Maybe someone should remind me that I fixed this in the lecture note. This is not 0, this is 1 because it starts from 1. The support starts from 1. And today we will focus on this one. Yeah? The number of trials needed until the... Actually, you don't actually need to write this. When you say until, it's automatically there. The number of trials what was that? The number of trials until the rth success. So we focus on that. And this will give us what we call the negative binomial distribution. You will come to know why we call it negative binomial. For the moment, you just follow the name. And remember, NB is just the notation. P is the probability of success in each trial. And this R represents that to get R successes, you need at least R trials. Yeah, you cannot have your rth success before the rth trial. Yeah, so it's following similar notation. Remember, we had for geometric, what did we do? We wrote GO. Here we wrote the probability of success in each trial, and there we wrote 1. 1 means that you need at least one trial to get your first success. Here we need to say that you need this is just a reminder. So if and I remember the notation used for geometric was K, yeah, when we were counting the trials, and if we only count the failures before the first success, we called it J, just a notation. Yeah. And just to remind us that it is something similar, instead of K, we will write K sigma. Sigma is for summation because we know it will involve the summation. And similarly for that J, we will have J sigma. So let's focus on K sigma. K sigma is now the number of trials needed to get your rth success, which means that if xi is the success indicator of trial I, or for trial I have to start from 1, and this is the number of trials needed. So if I sum it over that needed number of trials, I should get R. That's the meaning of rth success, which means that this summation must have R once included. The rest will be 0. So we need the distribution of K sigma. No problem. That trial K is the rth success, which means that you want to know the probability. The probability will be applied later on. That kth trial, in other words, I will need K, exactly K trials to get my R. Remember, this K sigma includes R in its definition. When I say K sigma equals to something, I mean that I'm looking for the number of trials, yeah, this one, the query point, needed to get R success. And here I can now replace this K sigma by its expression. Yeah, the expression comes here, that's actually no, it should not be that simple. That K trials are needed means that this K should be your last trial, and that's why I am now replacing that number of trials by this number of trials, because that is an open-ended equation. This is a fixed equation. You fixed it to a particular value and you have in mind. So now the definition allows me to require this event is the set of points which correspond to this summation. Yeah, K, remember, is the last trial. So the sum of successes, or the sum of ones, or the number of successes, should equal R. That's very similar to what we had for geometric. The only difference is that in geometric we had K is equal to 1. Now K can be anything. Now that is only possible if the last one, the kth trial must be the last one. So xk is the success indicator. For kth trial, that must give me a success if it is to be the last one. Yeah. But this time, if the last one gives me a success, in total, how many successes do I need in total? Can anyone tell me? I need R successes. The last trial, the kth trial, gives me 1. So here I must need how many successes? R minus 1. So now that summation for trial 1 up to K minus 1, I mean the previous trials, that must give me r minus 1, because if this is also r and that is also 1, then you will have r plus 1. We need r, yeah. So if this is 1, this has to
सर
be, yes.
सर हमने समेशन को k minus 1 तक क्यों देखें एक दफे बता दें
दोबारा बताएं आप।
ये हम समेशन में i equal to 1 से लेकर k minus 1 तक क्यों देंगे k तक क्यों नहीं हमें इसको रखा
ये k minus 1 की बात कर रहे हैं आप?
यस सर
नहीं तो आपको लास्ट पे सक्सेस मिल गया ना उधर, ये आप इसको कैसे इग्नोर कर सकते हैं?
अच्छा यानी लास्ट वो ट्रायल सक्सेस हुआ हमारा।
ये देखो ना, आप ओरिजिनल क्वेश्चन को पढ़े ना, नंबर ऑफ ट्रायल्स अंटिल द आर्थ सक्सेस। इसका क्या मतलब है कि जो आर्थ सक्सेस है वो आपको आखिरी ट्रायल पे मिलेगा। वो आखिरी ट्रायल नॉर्मली रैंडम वेरिएबल है, तो यहाँ पे तो अपर केस के लिख रहा हूँ। यहाँ मैंने अपर केस के को वैल्यू दी है स्मॉल के, ठीक है। अब इस स्मॉल के को आप अपने जहन में कोई वैल्यू इमेजिन करें। लेट्स से आपके ख्याल में के इज इक्वल टू 5 है। क्या है? 5 है, तो यहाँ पे 5 आ जाएगा
जी।
अब यहाँ पे आप ये कह रहे हैं कि फिफ्थ ट्रायल पे मुझे सक्सेस मिल गया, तो यहाँ पे भी आप 5 लिखेंगे, यहाँ तो 5 नहीं लिखेंगे ना फिर। इधर तो 5 नहीं लिखेंगे ना आप।
नहीं।
देखो मतलब यह है कि फिफ्थ पे आपको 1 मिल गया और जो पिछले 4 हैं उसमें आपको कितने सक्सेसेस मिल गए? r minus 1।
अच्छा
रिमेंबर ये बहुत जरूरी है, इस पॉइंट को समझना बहुत जरूरी है। यहाँ पे आपने एंड लिखा हुआ है, क्या लिखा हुआ है इधर? एंड का मतलब ये है कि दिस वन इज द लास्ट सक्सेस and here you have r minus 1 successes. If you add these two, you must get your r. You cannot have more than r successes, you cannot have less than r successes. That's a requirement of your equation. Similarly, the number of trials must also remain k. You cannot have less than k trials and more than k trials. So if that is the k trial, here you can only add up to k minus 1. You cannot have more trials. Now, what is the advantage of writing it in this way? Can anyone see? Of course, the support here will start from r and it can go up unbounded. If you think about the last one is simply an event and a Bernoulli setting. So it's a Bernoulli PDF, yeah, at 1 is success, p is the probability of success. Here it's remember when this was open, it was we didn't know it, yeah. Presenting, what is that? Stop presenting. Give control. I don't know what is wrong with this. Presenting, stop presenting. Maybe I must have some. Do you see any strange thing?
No sir, जो ऊपर नजर आ रही presenting give control.
Actually something is, what is it? Include, okay. Maybe something actually went on, so yeah, recording is going on. Just make sure that recording is going on. Okay. So let me minimize this. Okay, so when this k sigma was open, we didn't know what to do, but when we fixed this k, that k automatically fixed this k minus 1 as well. And when you have a fixed number of trials, yeah, here you have a fixed number of trials and a fixed number of successes, that points to which distribution? To binomial. Yes. And in binomial distribution, this is the notation for PDF. P is the probability of success. Here you write what? Here you write the number of trials. So how many trials do you have? K minus 1. Remember, we are now only focusing on this part, yeah? And here you write what? The number of successes. How many successes do you require? in that portion, r minus 1. So you are just using what you learned in the previous lecture. Yeah, you know how to plug the formula for this. You know how to plug the formula for this. You do these together, and you will get a nice expression for your PDF. PDF of what? Of your new random variable, which is your number of, what is this? This K sigma is the number of trials until the rth success. And this equation is only valid if K belongs to these values, support. Outside the support, this equation or this expression has no meaning. You can also approach this from another angle if you want. This was the direct approach. Yeah. And if you think about this, although we are using random variables, actually that's the whole point, that every time I forget to go full screen. Okay, so it's full screen. Although I am using random variables, but really this concept of multiplying these two things, it's still a probability. I'm still relying on events and intersection and so on. So can anybody see something here? If you remember, when we had binomial random variable, remember x was the number of successes. We wrote it as a sum of Bernoulli random variables. Do you remember that? We did that. And that allowed us to use the PGF and the convolution and the product of PGFs and so on. Can we do something similar here? Remember here, instead of x, we have this K sigma, which is the number of trials needed until the rth success. Now, in the previous lecture, and I think Momal also covered it in detail, we understood the independence, because these are independent trials that gave us a memoryless process. A memoryless process, which means that you can break this question of K, actually R, you are looking for R, K sigma looks for R successes. Yeah, this is the main thing. I'm looking for R successes, and I need the number of trials actually to get that. So I can break this down into looking for the next success. Looking for the next success. So if I define let me see if I have used that. Let's say if I define Ki or K1 as the number of trials needed for the first success. Are you with me? What will be the difference between these two? K sigma is the number of trials needed for the rth success. K1 is the number of trials needed for the first success. Now, if I now do something, let me show it visually. This is, I start at 0, and these are trial 1, trial 2, and so on. And let's say I am looking for that first success. So this random K1 gives me the number of trials needed for the first success. From that point onward, I start a new inquiry. Instead of starting it from 0, I start it from there. The number of trials counting from that point onwards till the next success. And let me call that K2. Let me call that K2. So K2 is not start counting from 0, it is counting from the point at which you got your first success. You're getting me this in this. So
Yes,
what if
sir.
I now add K1 and K2? What will I get? Anybody? K1 plus K2 will give me the number of successes, sorry, the number of trials needed for 2 successes.
Yes.
2 successes because I'm adding those two.
Yes,
K1
sir.
is for the first success, K2 is for the second, but after I observed my first success. So when I add this, there will be no overlap. That is made possible only by memorylessness, lack of memory. So if now tell me how many such variables should I need? Each variable is looking for the next success only. How many should I add to get my K sigma? How many? Tell me.
KR तक.
KR, because I need R successes. So I
Yes, sir.
turn my question of number of trials until rth success into R different questions. Each question is looking for just one success, and that success is the next one. And because we have a memoryless process, we don't care what happened before. Are you with me? So all these are, can you tell me the distribution of each one of them? They are distributed according to which distribution? They are all, come on. In each one you are asking for the next success. And that next success is just one success. And you are counting the number of trials until that happens. So all these are geometric random variables, isn't it? They are all?
Yes, sir.
They are all geometric and they all have the same probability P of success. And they are all independent. So we have everything that is needed for a PGF setting. So now instead of all this stuff, which may be too demanding for you, because we are relying the intuition, we are not relying on math here, we need to be very careful. Here you don't need to be careful. Here you just need to give everything to the math. You have a sum of our independent geometric random variables. You know the PGF of each one of them. Yeah, last time we calculated the PGF of each one of them, and actually they all will have the same PGF because P is the same. So I just need to multiply those PGFs because this is a sum of random variables. Sum of random variables is the convolution, the PDF, and the PGF is a product. So I just multiply and then I'm done with it. So let's do that here. That's exactly what I did. Let me repeat that argument. The lack of memory, it's very important. The lack of memory of geometric distribution implies that the number of trials ki plus 1 from success I. Remember, I got my ith success, and then I say, okay, the next one, the I plus 1 success. So from this point onwards, ki plus 1 is a geometric random variable. So I just add all these geometric random variables. They are all independent and they are identical. All have the same probability of success. All are geometric, yeah, with that distribution. And what do? I just multiply the PGFs. This is exactly what we did in the case of binomial distribution. Each one of these is PZ. If you don't get this, you go back to that lecture and you will see why this is true. And I have to raise this to R because I have R factors, one for each geometric random variable. That's it. If I want to now simplify this, if I want to recover my PDF, I can expand this and so on. What formula you need to expand this? Remember, if you want to write this in this form, z to kth, and something pk, what do you need? You need a binomial expansion because this is a constant. 1 plus something raised to r. This will, and why do we use the negative binomial? Can you see that now? Because this A plus B, which you are expanding, this is in the denominator. So if something is in the denominator, remember, normally you apply binomial expansion in this way. Yeah? You would never call it a negative binomial. But if you have it, if that is negative, then it will be a negative binomial. And why is that negative? Because this is in the denominator. A plus B is in the denominator. So are you getting this? That's the reason why it's called a negative binomial distribution. So, okay. Any question before I move on to the properties? Let me summarize what we did so far. We started with a sequence of Bernoulli trials, yeah, and we had Ki was the number of trials needed for the next success at stage I, and we have R stages, yeah, and if we add all of this, we will get the number of trials needed for R successes. Yeah, so we break this question into R questions. Or in other words, we break our random variable into R random variables. So just remember this, a negative binomial random variable, not the distribution, is a sum of geometric random variables. Yeah. Don't try to add PDFs, you're adding random variables. So I can now try to look for expectation of that. Instead of using PGF and all those strange formulas, I can simply note that K sigma is a sum of all these geometric random variables. Each one of them has the mean 1 over P. Just add it. 1 over P has to multiply how many times? R times. So R over P is my mean or expectation. How easy is that? Now the same reasoning allows us to work out the variance of this random variable. Remember, K sigma is a sum. It's a sum. Although here we did not need independence. Yeah. Here you can apply this to any sum, but here this is variance and this requires these to be independent. Luckily they are. So for each geometric random variable, I know the variance. I just add those variances. Yeah. So I just multiply by R because I have a summation of terms that are identical, so they will just multiply by R. So that was so easy. Now, another question that can arise is similar to what we had in geometric. Remember, in geometric we had two versions. One was the version K, which was the number of trials needed until the first success, and the other version was J, which was the number of failures before. The only difference between these two is that this counts the last trial at which you got your first success, and this doesn't count it because it's only counting failure. So if you think about it, this was simply K minus 1, yeah, because you subtract that last trial, because you're not counting trials, you're counting failures. Similar scenario happens here. If we have K sigma as the number of trials needed for the rth success, yeah, and if J sigma, you are still looking for that rth success, yeah, but you are not counting trials, you are just counting failures. So what will be the relationship between these two? Can anyone guess? If that was J equals K minus 1, you have to subtract one trial for the last success. What do you need to subtract here? Remember, these are trials, these are failures. So you have to subtract what? To turn these trials, number of trials, into number of failures before. You just subtract R, because each one of those R trials are successes, and you're not counting successes, you're only counting failures. And if you still cannot see that, let me change this. If I now write K sigma is the number of trials needed for R successes, and I can simply take this R to this side. So it will be J sigma plus R. Now what is this? This is the number of failures before, and this is the number of successes. If I add the two, what should I get? Number of trials. Yeah, so it's the same thing. If you still want to dig deeper into this, of course, here I change the notation. So instead of K sigma, I have J sigma. I still have negative binomial because it's a family, and P is the probability of success, and this 0 I can now start at 0 because I can have 0 failures. Yeah. Remember, if I get R successes, first trial success, second trial success, and let's say I'm lucky and all the first R trials are successes. So I got my R successes and R trials. So the value of that K sigma from previous slides will be R. But what will be the value of J sigma? Can anyone tell me in this scenario? How many failures did I observe before I got my 5 successes? This will be 0. So it can start with 0. K sigma cannot start with a 0 or a 1. It has to start with R. That's why I have that 0 as the subscript. This is not the power, this is subscript. Actually, it's not the exponent. I'm also calling it power. So it's not the exponent, it's just a subscript. So if you want to work it out that way, you need R successes. You are counting Xi this time is, of course, these are the Bernoulli success indicators. You are adding them. You start from 1, and you have to add R successes to the number of failures, because this time this is a failure. So you cannot write J sigma because you have to add all the trials. So if you work this out in a similar fashion, you can start with that event, plug values, and actually you get a formula like that. You see, this is something which you can work out. Actually, you translated an event in terms of J into an event in terms of K sigma, and that you already know the distribution for that, which is negative binomial with R, and you just use a shift. That's why it's called a shifted negative binomial. Remember, in geometric, this was called the shifted geometric random variable, and here this one is called the shifted because each time you shift the distribution. Yeah. And if you want, you can also work out its distribution. You see, this is also possible. If you want to check this math, that is something the only thing you need to notice here is that just instead of working all the math, I'm just focusing on the important pieces. J sigma is the number of failures before the R success. K sigma is the number of trials until the R success. So to go from number of trials to number of failures, I need to subtract R. And remember, I will know the PGF of this. So let's say the PGF of this is known. I know it from previous slides. And I need the PGF of this new quantity, which is new random variable. So you can see that to go from this to this, I have to multiply it by Z2 minus R. Why? Because of that shift. Yeah. Remember, I have Z squared, 1, all these things I'm adding. So because of this minus sign, it will have an impact on the exponents of z. You can verify this. You also see this, I think, in Laplace transform and in z transform and in Fourier series. This is shifting. Actually, this is also one of the reasons it's called a shifted version. And if you want to expand this, you see that negative exponent binomial expansion, and if you want, you can expand it like that. I would encourage you to read this just to know why we can express certain number of combinations as negative binomials. You see, even if you have a negative binomial, you can still apply the formula. You have been doing this, and remember, this is not something very fancy. If I give you, let's say, a1 plus x raised to minus 5, you know how to expand it, yeah? You would not say, oh, this is minus 5, I can't do that. You can still apply that formula, yeah? Minus 5, 1, x, and so on. So that's just a reminder of that. And similarly to the previous case, you can work out all the properties, yeah? Remember, this is now interesting. So this j sigma on one hand can be related to k sigma. Sorry, this is r. But you can do something. If you remember, we expressed k sigma as a sum of geometric random variables from 1 to r. Yeah, we did that. We should be able to do the same for j sigma. This is now the number of failures before the rth success. So if we break it down again into r questions or r random variables, and instead of counting trials, we just count failures. So I just write ji. So j1, so if I write j1 plus j2 up to jr, these are all, so this j1 is the number of failures before the first success. j2 is the number of failure before the first success. Because I'm only adding the number of failures, I should get the number of failures before the rth success. So it's very straightforward. You can use all that nice formula, sigma, expectation of sum of expectation, variance of sum of variances, independent, and so on. You see, this didn't change because a simple shift will not change the variance. A simple shift will change the mean. It did change the mean, but it did not change the variance. I would like to stop here for questions because the next topic is a bit different. So I would like to have questions now. Any questions so far?
सर एक ऊपर करेंगे सर.
हाँ?
स्लाइड ऊपर करें सर.
ये या ऊपर?
सर इससे थोड़ा सा ऊपर.
और भी ऊपर?
सर ये एक्सप्लेन कर दें सर, ये वाला पॉइंट, ये जो मैच इससे की हुई है.
नहीं, ये आप इस फर्स्ट लाइन की बात कर रहे हैं या नीचे, इससे नीचे मैं आ रहा हूँ?
सर वो स्क्रीन का ब्लर हो रही तो नजर नहीं आ रहा इसी तरह यहाँ पे.
आप दोबारा चेक करें, ये तो होना चाहिए. बाकियों को नजर आ रहा है ये?
सर आप नजर आ रहा है.
अच्छा, आपको किस लाइन पे मसला है ताकि मैं उससे स्टार्ट करूं?
सर यहाँ स्टार्ट करें जी ऑफ जे सिग्मा ऑफ जी, मतलब ये जो पूरा फॉर्मूला डिराइव हुआ है सर.
नहीं, मतलब
समझ नहीं आया.
फर्स्ट लाइन से बात कर रहे हैं, नीचे आ रहे हैं आप?
फर्स्ट लाइन से.
अच्छा, फर्स्ट लाइन से. एक्चुअली मैं यहाँ से, मैंने एक्सप्लेनेशन यहाँ दी है ना. मैं अगर इसको ऐसे करूं कि आपके पास, लेट मी जस्ट रिमूव एवरीथिंग.
तो लैग इतना आ रहा है कि वो समझ नहीं आ रहा क्या.
अच्छा, नहीं, आपको पीजीएफ का अगर फार्मूला पता हो ना, आप किसी भी, कोई भी, ये ना भी हो, मेरे पास जनरली जी एक्स होता है ना. जी एक्स ऑफ जी आप कैसे लिखते हैं? इफ यू रिमेंबर, you sum values of k, let's say from 0 to something, yeah,
जी,
and you write the PDF of x, at those
G.
values, and then you write z to the kth power. You do that. And
Yes,
let's
sir.
say I have a new variable y, which is x minus something. Let's say it is x minus r. I just use that same r so that you see it. Yeah. And now I want
Yes, sir.
now I want gy of z. Yeah. So
Yes, sir.
it will be, I will start with the same summation. Yeah. It will be fy of k zk. And now I want to express this in terms of the PGF of x. Now if you look at this fy of k, what is that? That is the probability that y equals k. Fine.
Yes, sir.
Now y I know is x minus r, so I can replace this with x minus r.
Okay.
And that minus r can go to the other side. So that will now become x equals k plus r. It will become x equals k plus r. Now here I have k. So normally for PGF, this thing must match that thing, yeah? If I want to make sense of it. So I would like to have that k plus r there as well, right?
Yes, sir.
Just like this, yeah? We had k there and we had k there. Now I am introducing z to plus r. So I must also introduce z to minus r to balance out, yeah? Because this is my own stuff, yeah?
Yes, sir.
And now I just need a change of variable. I will write k plus r as something, let's call it small j. This will become small j, limits will change, and I will just have z to minus r, and that is simply g x of z. That's exactly what we did there.
Okay, sir.
That's what you do in Laplace, that's what you do in Fourier, that's what you do in Z transform, everything. It's just a normal thing. So, and the rest
Okay.
is just math. Yeah?
Okay, sir.
And this is, if some of you want that, if you want to dig this deeper, actually this is whenever you want to expand something with a negative power, yeah, you know what to do, but there is an interesting relationship where a binomial coefficient with a negative upper part can be expressed by this formula, yeah. And if you work this out, this is nothing new. So this is, I mean, a reason why we call it negative binomial. But this is the negative part, yeah, negative binomial coefficient. But that's not important for you to understand each bit of it. So now let's go back to the first question. Let me go back to the first question. No, not the first question, those 4 quantities. So remember, we were done with this. This was distributed according to binomial with probability of P of success. No, 2 parameters with n trials and P as the probability of success. Similarly, this one was a geometric random variable starting from 1, P the probability of success. And we are now done with this, which is negative binomial. So we just train negative binomial, P again is the probability of success, and there it must start from R. And these had shifted versions. If instead of number of trials, if I focus on number of failures, then this will become GO0. And if I am here focusing on number of failures, I will have a shifted negative binomial starting with 0. Actually, there is another name which you will see in some books for negative binomial, and that is called the Pascal distribution. Pascal distribution. So whenever you see Pascal distribution, there is simply a negative binomial distribution. It's just a change of name. Now all these 3 were very easy to actually complete. This is a very difficult question. So here you are again counting the number of successes. So it's very similar to the first one. Yeah, as far as the number of successes is concerned, you have the same thing. You are counting the number of successes. Here you had a fixed number of trials. You also have a fixed number of trials. So changing n to r will not change the nature of the random variable. But here we need a condition now. This is required to have n success in a larger number of trials. And if you remember, I gave you the example of your GPA, CGPA. This is kind of, you're asking yourself, what should be, or how many times, for example, let's say success for you is A grade, yeah? Success for you is A grade. So in each subject you will either get an A grade or you won't get an A grade. Of course, a higher grade will also be a success. So you want to say, okay, if I want to complete my degree with, let's say, 15 A's, yeah, or A pluses, how many A's should I get in my first 4 semesters? So 1, 2, actually not 4 semesters. You will have to count each and every subject, yeah? First subject, second subject, and so on, in each subject. So that's actually an analogy where you fix the number of successes in a larger number of trials, and then let's move on to the math and you will see what I'm trying to achieve. Okay? This will give us what is called a hypergeometric PGF, but don't worry about the name. Just start with this combined space. Remember, we have a combined space of Bernoulli trials. And as before, this is the success indicator for trial I, which is Bernoulli distributed. We know it's Bernoulli distributed with probability P of success, all of them. Let's call S, uppercase S, subscript M. We need these subscripts to make sense of, because this is a very complicated example. So S is for summation. So we are adding the number of successes, number of actually ones. And we are counting the number of successes in how many trials? In M trials. Can anyone tell me what will be the distribution of this in that notation? Which family is this? Come on. Don't get trapped in the notation. It's just a simple question. I just changed something. So you should not bother whether this is M or whether this is S or subscript. This is what? Tell me. Number of successes in a sequence of M Bernoulli trials. This is binomial. And what should I write there for the number of trials? M. And for the probability P of success, I just write P. So binomial N, instead of N, I'm writing M, comma P. What is this? Number of successes in a shorter sequence of R trials. So what will be this distribution? Can anyone tell me?
Binomial.
It will still be binomial because I just changed M to R. So it will be binomial RP. Now the difference between these two is that this R is smaller than that M. So that M could be the long-term goal, like in your 8th semester. You can think of this R as 4 semesters. You can think of that M as 8 semesters. And this could be your overall CGPA or anything you are adding here. Let's say you are adding something in a semester. So maybe you are just counting the medals, yeah? So in each semester, you can declare your success as getting a medal, yeah? So in first semester, you get a medal, so x1 will be 1. You don't get a medal, x1 will be 0. Now, if this m is, let's say, 8, so S8 will be what? It will be the sum of S8 will be the number of medals you got in 8 semesters. Okay? And S4 will be the number of medals. And remember, I am only considering the semester medals. Yeah? I'm not considering the overall medals. So the number of medals in the after the fourth semester, or at the end of fourth semester. So now this last variable is very interesting. I come to this notation later on, but focus on this wording. What is this wording saying here? Number of successes in our trial. So in your case, it will be the number of medals. No, sorry, not the number of medals. Yeah, it is the number of medals. Yes, the number of medals in 4 semesters. Yeah, required for you to get a total of, let's say, can you give me a number? In 8 semesters, how many medals do you need? Let's say you need 6 medals.
Yeah.
So if you want 6 medals in total, how many medals should you get by the end of 4th semester? Remember this? This is still a random variable because you don't know how many medals. It doesn't mean that you will have to. Can you give me a few scenarios?
सर एक बार रिपीट करें सर या फिर
यहाँ पे मैं कह रहा हूँ कि मुझे टोटल अगर 6 मेडल्स चाहिए तो फोर्थ सेमेस्टर में मेरे पास डिफरेंट वैल्यूज हो सकती है ना. फोर्थ सेमेस्टर में कितने मेडल मैं ले सकता हूँ? इसमें अनसर्टेनिटी है अभी भी. बिल्कुल. असल में ये क्वेश्चन मैंने जरा ज्यादा सिंप्लीफाई किया है, बट you know that this is a very general question, so there is still randomness. This is actually random similar to that. इसमें और कॉम्प्लिकेशन आ गई है क्योंकि आपने कंडीशन डाल दी है आगे वाली. ठीक है. सो इट इज सम काइंड ऑफ प्लानिंग. ये मतलब जिस तरह आप गवर्नमेंट को सकते हैं कि 5 साल में अगर आपने ये अचीव करना है, हम जिस तरह पीटीआई की गवर्नमेंट पे आपको याद होगा ना, पहले साल के एंड पे प्रेशर पड़ा था ना कि आप 5 साल में जो आपने गोल्स अपने लिए डिसाइड किए हैं, आप हमें बताएं कि आपने साल में क्या किया है. तो दिस इज अ क्वेश्चन सिमिलर टू दैट. ठीक है.
यस सर.
So now let me go slowly, and that xi is definitely Bernoulli. It's very clear. This sm is binomial. That's also very clear. This sr is also binomial. Very clear. Now this is something I'm introducing a new notation, but there is a reason for that. Before that, I will just remind you that I have basically 3 parameters here. This random variable can only be specified if I know 3 things. One is that I'm looking for R successes, so that R must be written somewhere, and I have these 2 more parameters. I require n successes in m trials. So this n and this m can go as superscripts, yeah, n comma m, because that's the only way I can put it. And this R goes into the subscript. So are you with me now with this? This is just a way of reminding myself that I am looking for R successes, and sorry. No, R is not the number of successes. R is the number of trials. Yeah. So this Y will give me the number of successes. Yeah. Don't confuse it with negative binomial. Y will give me the number of successes, but this is not a normal Y. This R reminds me that I have only R trials available, and in addition to that, I put a condition that after this, if I go on, by the end of the mth trial, I must achieve n successes. That's the requirement. There is nothing random there. So,
Sir,
yes,
does this mean that SM is equal to N?
Sm is equal to n is a requirement. You want this.
Okay.
If this is not true,
Okay.
this random variable is not defined. ये बात समझ आ रही है? अच्छा, अब मुझे एक बात बताएं.
Yes, sir.
मेरे पास एक रैंडम वेरिएबल है. इसके अलावा जनरली आपके पास नॉर्मली जब रैंडम वेरिएबल होता है तो जब आप ये लिखते हैं x is equal to let's say 3, what do you mean by this? नॉर्मली हम ये ब्रैकेट भी लिख लेते हैं. ये क्या होता है? आप इसको क्या कहेंगे इस चीज को? नाम इसका क्या है? It is n. Anyone? It is n. इवेंट है या नहीं है? क्योंकि इस इवेंट में बेसिकली वो सारे एलिमेंट्स है सैंपल स्पेस के. Remember, I'm just reminding the theory. All the elements of the sample space, to which, because there may not be a single element, there may be many elements, more than one, to which x has assigned which value? 3. That's the meaning of this. This is a shorthand. When I write x is equal to 3, this is not an equation. This is just a shorthand for the subset of my sample space, which is an event, and all those elements in that event, what they have in common is that the random variable has assigned a single value to that. Similarly, if I replace this with, let's say, less than or equal to 3, I have to change that condition into less than or equal to 3. Are you with me? And there was even an alternative notation. This is basically a pre-image, and remember I use this square notation, square bracket, and I can use that as well. If I, let's say, go back to equal to 3 and equal to 3, I can make a subset, a Borel set, bracket, pre-image. So that's actually the main thing. So if you understand this M equal N as an event, and for your convenience, I'll simply call it A, just so that you know that it is an event. It is not an equation. An event of the sample space. I can even write it for you. It is an event of the sample space. Now there is, any function f has a domain. Let's say it has a domain D, and it has a codomain, let's say, or maybe if you call it range. This is normally your definition of a function. But sometimes you need to have a restriction on this function. What? Which means that you will only be, you define a new function which will be defined not for all values of D, but only for some values of D. Can you give me an example of this? You have done this in math. Can you give me an example of a mathematical function where for some reason you must restrict it to a subset of the domain? Let me give you an example. Do you remember sine function?
Yes, sir.
Sine function को मैं इसी नोटेशन में लिखना चाहता हूँ. कॉलन, यहाँ पे मुझे बताए यहाँ पे डोमेन इसका क्या है? रेडियन में बताएं मुझे.
-π to π.
Sine function, sine of theta.
Sine of theta.
डोमेन क्या है इसका? रियल लाइन है या नहीं है? बिकॉज साइन ऑफ एनी रियल नंबर इज वेल डिफाइंड, या कोई मैं गलत बात कर रहा हूं? रेडियन में, रेडियन की बात मैं कर रहा हूं, ठीक है। और रेंज इसका ये क्या है? ये भी रियल लाइन है, लेकिन अगर आप सिर्फ फोकस रखना चाहते हैं तो इट इज बेसिकली बिटवीन -1 एंड
1
+1। ये बात समझ आ गई आपको?
yes
अच्छा, मुझे
yes
इसका इनवर्स चाहिए, मुझे साइन इनवर्स चाहिए, तो फिर गड़बड़ हो जाएगी।
जी
गड़बड़ होगी या नहीं होगी?
होगी सर।
तो उस गड़बड़ को रिमूव करने के लिए मुझे इसको रिस्ट्रिक्ट करना पड़ेगा।
-π/2 to π/2
हाँ, अब आपको समझ आ गई है?
जी
आई डिफाइन, और उसके लिए इवन नोटेशन भी डिफरेंट है। ये स्मॉल एस लिखते हैं और उसके लिए आप क्या लिखते हैं? ये एस को आप कैपिटल लिखते हैं। याद आ रहा है आपको?
थोड़ा बहुत
ये एस को जब आप कैपिटल लिखते हैं, इसका मतलब ये है कि ये फिर सिर्फ -π/2 और π/2 के दरमियान है।
yes sir
This is what we mean by restriction of a function to a subset of the domain। ठीक है, मैं एक और एग्जांपल भी दे सकता हूं आपको, बहुत आसान। आप स्क्वायर लेते हैं ना, लेट्स से SQ, ये नाम है स्क्वायर फंक्शन। तो अगर इफ यू रिस्ट्रिक्ट इट, लेट्स से आई रिस्ट्रिक्ट इट to positive only, so positive only, non-negative, sorry, then I can actually take the inverse and so on. So this is nothing new basically. So now you should know there is actually a notation in mathematics where you take a function, yeah, and normally this function can have any domain, but you want to restrict the definition of that function. You want to have a new function, let's call it f star, which will be restricted to a subset. So let's call that subset A. Let's call that subset A. So you just, between these two, because this is a function, this is a domain, you just write this symbol. Yeah, it looks like 1, but it's not 1. Sorry, I did it wrong. It's the other way around. You have this straight line and it looks like a hockey stick, yeah? It looks like a hockey stick. So whenever I have a function, and remember this set has to be written down, yeah? It's a subscript. In between I have this thing, you can call it whatever you want. Actually it's called the restriction symbol, yeah? So if you understand this, now tell me what have I tried to do here? Can anyone tell me now? I told you this Sm is equal to n is what? This is an event.
an event.
So I am restricting that Sr, which is normally free. That Sr is a free variable. It's just the number of successes in R trials, no further conditions. I am putting a restriction on that.
Yes.
In other words, because it is a random variable, because this is important to understand, okay? Because it is a random variable, इसका domain क्या होगा? SR का. Can you tell me इसका domain क्या होगा? Or any of these random variables, किसी भी random variable का domain क्या होगा? Tell me.
Support नहीं होती सर?
हाँ? Support domain नहीं होता, वो उसका range होता है. Domain sample space होगा ना?
Yes.
Because it applies to points of the sample space. ये आपको real line पूरा देता है. कोडोमेन इसका real line है, support नहीं है.
Okay sir.
क्योंकि real line पे आपको बाकी points पे भी probabilities चाहिए ना empty set के लिए. So basically now what I want is that I want a new function which is not defined for all of the omega, it will be defined for a subset. That is what I represent by this thing, SR और इस ट्रेंड सिंबल, और यहां पे मैं क्या लिख रहा हूं, A लिख रहा हूं. अब उस A की जगह अगर मैं ये लिख दूं तो मैंने कोई नई बात नहीं की है. I know that SM is equal to N is an event. या तो मैं उसी SM is equal to N को यहां पे क्या लिख रहा हूं, as in. So it looks very strange, but it's very perfect. It's not rocket science. It's not something complicated. ये बात समझ आ रही है?
Yes, sir.
I am restricting my sum of Bernoulli random variables. Remember, this is a sum. So actually, I can go on with this. It is still a sum of X Bernoulli random variables. Sorry, of R Bernoulli random variables, but with a condition, with that I must restrict it only to outcomes. Remember, I am restricting it. ये ऐसा ही ना, आपको एक दफ़ा मैंने एक बात बताई थी कि आप कंडीशनल प्रोबेबिलिटी को मोटिवेट करने के लिए कि आप लेट सपोज आप वो खेल रहे हैं लूडो, और आपको जब तक 6 नहीं मिलता आप गेम स्टार्ट ही नहीं कर सकते, ठीक है?
Yes, sir.
तो आप उस 6 को रिस्ट्रिक्शन के तौर पे ले सकते हैं ना.
जी sir.
मतलब ये मैं आपको ऐसे लिख सकता हूँ कि नॉर्मली आप लिखते हैं P of A given B. ये आप क्या लिखते हैं, प्रोबेबिलिटी. Yeah, but you can also do it like that. You just write P of B, no problem, but this P is wrong. This P is not the function. It must be restricted to A. Sorry, it's actually I did it the other way around. अगर मैं आपको ये समझा दूं ना कि it is still a probability of A, I'm still looking for the probability of A, but if I restrict P to B, so I will get P of A given B. That's actually a better explanation of this notation. P of A given B, ये given B में restriction यहाँ पे लगा रहा हूँ, P को मैं free छोड़ रहा हूँ. यहाँ पे मैं क्या कर रहा हूँ, वहाँ पे मैं कुछ नहीं लिख रहा, मैं P के ऊपर restriction लगा रहा हूँ कि P will not be defined everywhere, it will be a restriction. Actually इसमें थोड़ी सी गड़बड़ है, क्योंकि ये मेरे हिसाब से इसलिए गलत है क्योंकि P is not a function from the sample space. Yeah, P is a function from the event space, so that was not a good analogy. Okay, अगर ये बात आपको समझ आ गई है तो now we can attack this problem. अच्छा, इसको हम एक और एंगल से भी देख सकते हैं. Some people actually don't like this. We can have another go at this. Can anyone try to look at this quantity? In other words, look at this condition. Can you see this from a totally different angle? इसमें एक गड़बड़ मैं बता रहा हूँ, गड़बड़ क्या है. इन दोनों में जिनको आप सम कर रहे हैं ना, इसमें भी समेशन इन्वॉल्व है, SM में भी समेशन इन्वॉल्व है और SR में भी समेशन इन्वॉल्व है. और इस समेशन में सारे वेरिएबल्स क्या है जिनको आप ऐड कर रहे हैं, सारे क्या हैं, मैं लिख रहा हूं, ये सारे क्या हैं, इंडिपेंडेंट है. मुझे ये बताएं कि यहां पे भी समेशन आ रही है ना, ये समेशन है ना बेसिकली, सिर्फ आपने इसको रिस्ट्रिक्ट कर दिया. Will these be independent? Yes or no?
No sir.
क्यों? क्योंकि वो जो कंडीशन आप डाल रहे हैं वो मसला करेगा ना, वो कंडीशन आप डाल रहे हैं वो मसला करेगा. ठीक है, ये ऐसे ही है. वो CGPA वाले एग्जांपल में देख ले, आपने टारगेट किया हुआ है कि मैंने 6 मेडल लेने हैं और आपको फर्स्ट सेमेस्टर 2 सेमेस्टर में मेडल कोई नहीं मिला, तो आप आगे वाली प्रोबेबिलिटीज तो चेंज हो जाएंगी ना आपके लिए.
जी सर.
तो अब ये इंडिपेंडेंट तो नहीं रहे ना. तो इसका मतलब ये है कि we should now think of an experiment, so we should stop actually pretending that we have independent trials. ये क्या है? बर्नौली ट्रायल्स है ना?
जी सर।
अब हमारे पास एक ऐसा वेरिएबल आ गया है कि जो बेसिकली बर्नौली ट्रायल पे है ही नहीं. It is defined, it is still defined on experiments, experiment 1, experiment 2, experiment 3 and so on. I still have R experiments, yeah, I still have R experiments, but all, those experiments are now dependent on each other. So इसका मतलब
Yes,
ये
sir.
है कि वो डिपेंडेंस मैंने अभी क्रैक करनी है कि वो डिपेंडेंस क्या है, वो डिपेंडेंस क्या है.
Yes, sir.
So let's try something, and I want you to be creative. You can look at this as the number of successes in R draws, क्योंकि ये डिपेंडेंस की एक एग्जांपल आपको याद है, सैम्पलिंग, जब हम काउंटिंग पढ़ रहे थे तो वी हैड सैम्पलिंग विद रिप्लेसमेंट एंड वी हैड सैम्पलिंग. आपको ये भी याद होना चाहिए कि सैम्पलिंग विद रिप्लेसमेंट में प्रोबेबिलिटीज चेंज नहीं होती तो वो इंडिपेंडेंट केस बनता है, और सैम्पलिंग विदाउट रिप्लेसमेंट में क्या बनता है? डिपेंडेंट बनता है. सो अभी आपको ये इंटरेस्टिंग लगेगा कि ये बेसिकली सैम्पलिंग विदाउट रिप्लेसमेंट का ही केस है. समझ आ गई? सो इमेजिन यू हैव ए बॉक्स, या, एंड लेट्स से दैट बॉक्स हैज m ऑब्जेक्ट्स. हाउ मेनी? m. ये बिल्कुल वो सैम्पलिंग, वो जो काउंटिंग टेक्निक्स की तरफ हम वापस जा रहे हैं. I have m objects, and let's say out of those m objects, n of them are of my interest, so I will call them favorable. I want them, so it's like medals, yeah? It's like your medal. और बाकी कितने बच गए टोटल? अगर m है और ये n है तो ये कितने हो गए टोटल बाकी?
M minus n.
m minus n. So ये m minus n मुझे नहीं चाहिए. It is anything other than the medal, yeah? So imagine आप पहला ड्रॉ कर रहे हैं. क्या कर रहे हैं? एक एलिमेंट आपने ड्रॉ किया. रिमेंबर आपने बेसिकली टोटल कितने एलिमेंट ड्रॉ करने हैं? R. तो पहले ड्रॉ में आपके सक्सेस की प्रोबेबिलिटी क्या होगी अगर फेवरेबल n है तो? कोई बता सकता है?
n divided by m.
n divided by m. That is your probability of success in the first trial. Let's say this one is the first trial. और जो 2 है सेकंड ट्रायल में, सेकंड ट्रायल में जो प्रोबेबिलिटी ऑफ सक्सेस होगी, अगर आपको ये पता चल जाए कि फर्स्ट में क्या हुआ है तो ये n by m नहीं होगी, ये चेंज हो जाएगी. समझ आ गई? क्योंकि ये विदाउट रिप्लेसमेंट है. जब विदाउट रिप्लेसमेंट है तो वो तो n और m तो चेंज हो जाएंगे ना.
Yes,
Are you
sir.
following me?
Yes, sir.
अच्छा, इसका मतलब ये है कि I can now look at this as ये जो y r n m था, I can look at this as the number of successes in R draws, and these draws are not independent, they are independent because it's sampling without replacement, from a set of m objects, n of which are favorable. Favorable इसलिए मैं लिख रहा हूँ क्योंकि इसको मैं success के साथ connect करना चाह रहा हूँ. We could then express this as a sum of dependent RVs, not a sum of independent RVs, but a sum of dependent RV, and let's call them Ki. So I'm still adding K R random variables, but this time Ki is the success indicator, and I'm now writing call. I'm trying to write a different name. It's called draw I. I'm not writing trial, क्योंकि trial आपको याद है, trial हम तब लिखते थे जब वो identical experiments होते थे. क्या होते थे? ट्रायल वर्ड हमेशा अब तब यूज करते हैं जब आप एक एक्सपेरिमेंट को बार बार यूज कर रहे हैं और उसकी रैंडमनेस चेंज नहीं होती. बर्नौली ट्रायल, रैंडम ट्रायल, ठीक है. ये चूंकि वो ट्रायल नहीं रहे तो मैं इसको ड्रॉ या आप इसको एक्सपेरिमेंट कह सकते हैं. यू कैन कॉल इट एनीथिंग बट यू कैन नॉट कॉल इट ट्रायल बिकॉज दीज आर नाउ एक्चुअली you had the same experiment and you were repeating it. Now you have different experiments. Each draw is a different experiment. Try to understand this, okay? अब मुझे ये बताएं कि जो प्रोबेबिलिटी ऑफ K1 is equal to 1 क्या होगा? Do you agree with this? क्योंकि K1 क्या है? Success indicator है ना? Its value will be 1 or 0. 1 for success. So it is still a success indicator. 0 for failure. आपने सिर्फ वो बर्नौली वाली कहानी खत्म कर दी ना? समझ आ गई?
Yes sir.
तो
Yes sir.
P of K1 is equal to 1 का मतलब ये है कि the probability that the first draw is a success, n by m.
Yes.
You already told me. What will be what will be the probability of failure on the first draw? M minus n over m. ठीक है?
Yes.
Add the two and you should get 1, yeah? You should get 1.
Yes sir.
अच्छा, अब अभी भी इसमें डिपेंडेंस नजर नहीं आ रही ना? So डिपेंडेंस को जरा चेक करते हैं. Let's check the dependence among the first two draws. So remember, this is now a conditional probability. क्या? Now,
Yes sir.
the probability of getting a success on the second trial or the second draw, sorry, trial में गलत word use कर रहा हूँ. This probability of a success in the second draw, given that I had a success in the first draw, do you agree with me that it will be n minus 1 by m minus 1? क्योंकि दोनों कम हो गए ना? Success भी एक कम हो गया.
Yes sir.
Available और ये number of elements भी कम हो गए. Now, don't change the first draw. Condition it still on the success in the first draw. But now you are looking for the probability of a failure in the second draw. This will still be m minus 1. क्योंकि total तो change हो गया है ना? This will not change. क्यों? ये उधर भी m minus n था, इधर भी m minus n है. Can you explain that? ये क्यों चेंज हुआ, ये क्यों चेंज नहीं हुआ?
Because we had a success
Huh?
in the first round. We didn't have
Sorry?
any failures. We didn't have any failures.
क्योंकि फर्स्ट में सक्सेस हुआ है ना, और आपको क्या चाहिए? आपको फेलियर चाहिए. फेलियर तो अभी हुआ नहीं है. तो जो इनिशियल अवेलेबल थे, नंबर ऑफ फेलियर जो पॉसिबल थे, वो उतने ही है, वो चेंज नहीं हुए. ठीक है? अच्छा, यहां पे क्या है? इधर given that the first was a failure, the first draw, now you want to know the probability of a success in the first draw. अब ये चेंज नहीं होगा, ये n का n ही रहेगा, क्योंकि पहला फेलियर था, तो अभी सक्सेस तो शुरू ही नहीं हुआ ना. तो टोटल तो चेंज हो गया, टोटल नंबर ऑफ एलिमेंट्स, लेकिन नंबर ऑफ अवेलेबल सक्सेसेस इज स्टिल n. जो शुरू में था वो अभी भी n ही है. समझ आ गई बात?
Yes sir.
और लास्ट
सर मेरा एक क्वेश्चन है.
यस.
सर इसमें probability of success and failure should be equally likely.
नहीं, इक्वली लाइकली हो नहीं सकता ना, क्योंकि ऊपर हमने सिनेरियो डिफरेंट चूज किया है ना. सिनेरियो क्या है? I imagined a set of elements, और उस सेट में कितने एलिमेंट्स हैं टोटल?
नहीं सर, वैसे जो हर ड्रॉ की बात
नहीं, ड्रॉ में देखो ना,
जब हम
सक्सेस
ये
और
यूज
फेलियर,
करते हैं, जब
सक्सेस और फेलियर.
कार्डिनैलिटी वाली चीज यूज करते हैं.
नहीं, दोबारा बताएं आप.
सर जब हम कार्डिनैलिटी की बात करते थे कि टोटल नंबर ऑफ जैसे
हाँ, तो मैं वही कार्डिनैलिटी में यूज कर रहा हूँ, लेकिन वो कार्डिनैलिटी चेंज हो रही है ना.
जी वो तो चेंज हो रही है, लेकिन
मुझे एक बात बताएं, ये समझना बहुत जरूरी है. स्टार्ट में इनिशियली आई हैव अ सेट ऑफ m ऑब्जेक्ट्स, जिसमें n मेरे काम के हैं, जिसको मैं फेवरेबल कह रहा हूँ. तो अगर उनमें से कोई ड्रॉ में उनमें से निकल आया, उसको मैं सक्सेस कहूंगा. अगर m माइनस n में से आ गया, मैं उसको क्या कहूंगा? फेलियर. पहला ड्रॉ मेरे पास आया है, तो आप डू यू एग्री विद मी दैट दीज टू विल बी डिफरेंट? सक्सेस और फेलियर की प्रोबेबिलिटी डिफरेंट होगी, या आप समझते हैं कि ये दोनों सेम होंगे? ये दोनों
नहीं, ये दोनों तो फर्क होंगे.
अच्छा, अब यहाँ पे आ जाएं. यहाँ पे रिमेंबर, ये जो क्वेश्चन है ना, हर एक प्रोबेबिलिटी का जो क्वेश्चन है, ये इंडिविजुअल ट्रायल है, ये सम की बात नहीं हो रही है. सो यहां पे मैं ये कह रहा हूं द प्रोबेबिलिटी दैट आई हैव अ सक्सेस ऑन द सेकंड ड्रॉ, और ये अनकंडीशनल नहीं है, ये कंडीशनल है। आप जो चाह रहे हैं ना, आपके जहन में जो आ रहा है वो अनकंडीशनल है। लेट्स से मैं ये क्वेश्चन, आप शायद आपके जहन में ये आ रहा है प्रोबेबिलिटी दैट K2 इज इक्वल टू 1, आप शायद इसकी बात कर रहे हैं। दिस विल नॉट चेंज,
ठीक है।
ये कंडीशनल है। कंडीशनल का मतलब ये है कि पहला सक्सेस आपको मिल गया है, तो स्टार्ट में आपके कितने सक्सेस के लिए कितने एलिमेंट अवेलेबल थे? n। फर्स्ट में एक निकल गया तो n-1 हो गया ना। ये विदाउट रिप्लेसमेंट को आप कैसे डालेंगे अगर ये आप ये नहीं कर रहे हैं तो? समझ आ गई ये कंडीशन? हाँ सॉरी
जी सर।
समझ आ गई अब या अभी भी नहीं आई?
सर मैं मेरे ख्याल से इस चीज़ से कंफ्यूज हुई हूँ कि जैसे हम उसमें से बॉल पिक करते हैं एक अर्न में से, सो इफ इट्स विदाउट रिप्लेसमेंट तो वो कम तो होता जाता है। ऑब्वियसली प्रोबेबिलिटी ऑफ अ रेड बॉल चूज होने की चेंज होगी प्रीवियसली कोई भी चूज हुआ। इट्स जस्ट कि जितने टोटल हैं एट गिवन टाइम
नहीं,
उसके लिए तो
ये
हम
गिवन
इक्वली
टाइम
लाइकली
यहाँ
करते
पे
हैं
क्या
ना।
है? ये सेकंड ड्रॉ है ना, ये गिवन टाइम
हाँ
आपका
बिल्कुल
सेकंड ड्रॉ है और फर्स्ट
बिल्कुल
ड्रॉ
बिल्कुल
हो
आप
चुका
सही कह
है।
रहे हैं। व्हाट आई एम सेइंग इज के एक ड्रॉ में करंटली अगर हम देख रहे होते हैं तो जितने बॉल्स लेट्स से अगर
नहीं,
मैं
वो
इसको
आपकी बात
बॉल्स के
बिल्कुल
साथ
ठीक है,
कर रही
लेकिन
हूँ
वो एक ड्रॉ
तो
रहा नहीं ना।
उस
ये
टाइम
कंडीशनिंग जब आप करते हैं तो ये क्वेश्चन दो ड्रॉस के बारे में है, ये एक ड्रॉ का क्वेश्चन नहीं रहा।
सर वो बिल्कुल ठीक है। सेकंड बेशक कंडीशनल भी हो जाए, व्हाट आई एम सेइंग कि लेट्स से एक रेड बॉल निकल गया है उसमें से, तो
हाँ
कंडीशन हो गया ना कि पहला रेड बॉल आ गया। अब जो रिमेनिंग है उनमें से पिक होने की तो इक्वली लाइकली होती है ना प्रोबेबिलिटी।
हाँ हाँ, अच्छा अच्छा, आप वो
मतलब
कह रहे हैं इक्वली,
हाँ
तो इक्वली
जी
लाइकली की वजह से तो हम रेशो ले रहे हैं ना।
हाँ बिल्कुल दैट्स व्हाट आई वाज
ये
सेइंग। हाँ
रेशोस,
बिल्कुल ठीक है सर।
अच्छा आप ये पूछना चाह रहे हैं ये
जी
सारे
जी
रेशोस, बेसिकली इट्स अ गुड क्वेश्चन। ऑल दीज रेशोस बेसिकली, चाहे ये रेशो है चाहे ये रेशो है, ऑल दीज रेशोस आर बेस्ड ऑन इक्वली लाइकली। वो उस पर कोई क्वेश्चन नहीं है, वो आपकी बात बिल्कुल ठीक है। अच्छा, मैं असल में आपकी क्वेश्चन को कुछ और समझ रहा था। सो अच्छा, अब मुझे ये बताएं, यहाँ पे हम आगे अगर जाएंगे तो ये जरा कॉम्प्लिकेट हो जाएगा ना, क्योंकि इट विल गेट वेरी कॉम्प्लिकेटेड। लेकिन मैं एक चीज आपको बताना चाहता हूं, ये तो मैंने स्टार्ट में किया है ना K1, अगर ये मैं K2 के लिए कर लूं, ये क्वेश्चन किसके लिए कर लूं? K2 के लिए क्या होगा ये आपके ख्याल में? इसको आप मैथमेटिकली चाहें तो आप बिल्कुल वो कर सकते हैं ना कि आप इसको टोटल प्रोबेबिलिटी लगा दें, पहले K2 इज इक्वल टू 1 गिवन K1 इज इक्वल टू 1 कर दें। आप बेसिकली इन दो सिनेरियोस को देख लेना, इन दो सिनेरियोस को आप क्या कर लें, देख लें, और लॉ ऑफ टोटल प्रोबेबिलिटी अप्लाई करें। अप्लाई करेंगे, यू विल बी सरप्राइज टू नो दैट द आंसर इज स्टिल n ओवर m। और इसकी जो नॉन मैथमेटिकल एक्सप्लेनेशन है वो ये है कि चूंकि आप कंडीशन कर नहीं रहे, तो सारे ट्रायल्स जो है ना, उस केस में सिर्फ कंडीशनिंग में विदाउट रिप्लेसमेंट आ रहा है, विदाउट कंडीशनिंग कुछ भी नहीं हो रहा। ठीक है? सो इन अदर वर्ड्स, these, although you see only these 4 pairs, all of the pairs will have the same likelihood. For example, अगर मैं ये K2 K1 की जगह ये मैं K3 K2 कर दूं, इसको मैं K3 कर दूं और इसको मैं K2 कर दूं, ये चेंज नहीं होगा, क्योंकि इसमें मैंने वो K1 को तो निकाल दिया ना। ये समझ आ गई? इसकी जो मेमोरी है, ये मेमोरी लेस तो नहीं है ज्योमेट्री की तरह, लेकिन जो इसकी मेमोरी है वो सिर्फ पिछले पे है। आपको याद है ना, एक दफा मैंने एक नेटवर्क भी शो किया था कि फर्स्ट ट्रायल सेकंड को इन्फ्लुएंस कर रहा है, सेकंड थर्ड को कर रहा है, थर्ड फोर्थ को कर रहा है, लेकिन थर्ड को फर्स्ट इन्फ्लुएंस नहीं कर रहा, थर्ड को सिर्फ सेकंड कर रहा है। ठीक है? बट इट इज नॉट वेरी इजी टू डील विद। वी नीड to get back I'll come to this later, yeah. ये मैं आपको सिर्फ समझा रहा था कि there are two ways of looking at it. You can either look at it as a sum of dependent random variables, ठीक है, as a sum of, or you can look at it as a sum of independent random variables with this restriction in mind. ये ज्यादा आसान होगा. कितना टाइम हमारे पास रह गया अभी?
हो गया टाइम, आई थिंक
टाइम हो गया, ठीक है. बस चलो ठीक है, मैं इसको हम बाद में कंटिन्यू करेंगे. बट बिकॉज आई अपलोडेड दिस, सो आई वुड लाइक यू टू रीड दिस डॉक्यूमेंट, क्योंकि नेक्स्ट टाइम मैं नहीं चाहता कि इस पे हम ये चीजें दोबारा रिपीट करें. और आप बीच में आपका कोई सेशन होगा मुमल, या वो अगले हफ्ते होगा?
सर मेरे ख्याल से मतलब ये थोड़ा कवर हो जाए, फिर अगले हफ्ते कर लेंगे.
अच्छा ठीक है, चलो ठीक है. बस बट इट्स वेरी इंपॉर्टेंट दैट यू रीड दिस बिफोर फ्राइडे, क्योंकि हम इसको नेक्स्ट लेक्चर में कंक्लूड करेंगे इंशाल्लाह.
सर वो आखिरी वाला पॉइंट दोबारा बता देगा, जब केस इक्वल्स टू 3 का वो वाला.
कौन सा वाला? अच्छा ये मैं कह रहा हूं कि अगर उसको रिप्लेस कर दूं. नहीं, आप क्वेश्चन दोबारा पूछ लें.
सर आपने बोला था ना कि अगर हम ये, जैसे हमने कंडीशन थी 4 कंडीशन, जब केस इक्वल्स टू 2 था और जब के गिवन के केस इक्वल्स टू 1 हो चुका था, मतलब के K1 हो चुका था, तो आपने बताया था ना दोबारा कि अगर के जब 3 की बारी हुई, थर्ड ट्रायल की बारी आई,
ठीक है. अच्छा नहीं, मैं वो बता रहा हूँ. हाँ, ये इसको मैं इसको हम नेक्स्ट टाइम डिस्कस करेंगे, क्योंकि इसमें असल में मैं एक चीज मैंने स्किप की है. आई थॉट कि यू विल गेस दैट विदाउट द मैथ, लेकिन शायद वो मुझे वो डेरिवेशन आपको शो करनी पड़ेगी. ठीक है. फिलहाल आप सिर्फ इसको समझ लें कि इनिशियल प्रोबेबिलिटीज क्या हैं और फर्स्ट टू ड्रॉस क्या हैं. जस्ट टू prepare you for the next lecture. Interestingly, these probabilities will not change if you go from it is not memoryless, but it is a special type of memory where you only remember the immediate the most recent past. So K3 will depend on K2, but it will not depend on K1 directly. वो K1 की डिपेंडेंस K2 में आ चुकी है, वो बार बार नहीं आएगी. ये इंशाल्लाह हम इसको डिस्कस कर लेंगे.
यस
ठीक.
ओके.
ओके.